So, thank you for such a warm welcome. So today we will be speaking about bugs that we can find in Java and basically other stuff that Oracle doesn't want you to know about. My name is Grzegorz Piwowarek. I'm blogging at forcomprehension.com. I'm also a lead backend engineer at Casumo on Malta, working remotely there. And I do also trainings for Bottega IT Minds. Plus, I did some open source contributions. So, the Java 8 was a very interesting release in the whole history of Java. As far as I remember, Mark Reinhold, one of the chief architects of Java, kept saying that Java would never get Lambda Expressions and would never go functional. And the reason for that was that they wanted actually to avoid cluttering the language. But it turned out that, as you can see, this kind of mindset changed over time, and Java is adopting so many functional ideas, basically copying a lot from Scala and Kotlin to make sure that they keep up with the competition. So the release was very special because we got Lambda expressions, we got some functional abstractions, and it was one of the most important releases ever, at least in my opinion. But then quite a lot happened, because if you remember those like old times, how many years would you need to wait for a new Java to be released? 3, 4, 5? How many years did we wait for Java 8? 5? And now it's like Java 12 will be released just in, I think, in 5 months from now. So things are going pretty fast. So here comes a question for you. How many of you have already adopted on production the Java version higher than 8? Is anyone that has 1, 2, 3, 4, 5? 5? OK. So this is the problem. When Java 8 was released, everyone pretty much jumped into it. They wanted to try lambdas and stuff. But now, suddenly, if you look at different surveys, it turns out that we are already on Java 11, but many people have not already migrated above 8 and stuff. What's the reason for that? Probably because the main promise of Java was somehow broken, because the Java was promised to be backwards compatible. But it didn't work that nicely with the module system. It was very painful to migrate because of that. And I have a feeling that many people don't need to migrate beyond 8 because they might say that they don't need module system, they don't care about local variable type inference and stuff. And there is something in that. But again, let's have a look at the Java release cycle and see what changed recently, because features is not the only thing. Recently, there was a very big change, because in the past, Java releases were driven by big features. So in Java 8, for example, it was Project Lambda. Java 9 was revolved around modularity. Well, Java 7 had strings in switch statements. So we got all those very big breakthrough features all along the time. But now something changed. Now the Java release train is cadence-driven. So the train keeps going, and every 6 months we get a release out. And this is a very big change, because suddenly it turns out that all those small features that were blocked by big features can go out relatively quickly. So this is why we got Java 9, Java 10 every 6 months, and then Java 11, and we'll have in March Java 12 already. But there is one important thing to remember. Those were not all made equal. Because we have Java 7, Java 8, those were long-term releases, but Java 9 and 10 were minor feature releases, where actually were only released so that you can jump in there, check if your things work, get acquainted with new features, but they were very short-lived. So if you look at Oracle, you can't even download Java 9 and Java 10 anymore. Well, because they are dead. You need to, if you want to migrate beyond Java 8, you go straight for 11. And the next big Java release will be Java 17, 3 years from now. So once we know that, let's have a look at a few things that you should probably know regarding what went bad in Java 8. So let's start with first a very trivial and simple example. Conditional stream termination. So imagine you have a simple list of dates, where those dates are arranged in chronological order. And we have a very simple task. We want to take all dates before certain date. Well, that's a very easy task, right? Because you can create a stream, and you can declaratively use the filter method and tell which dates do we want, and then do something with that. Does it work? Yes. But there's one problem with that. Because apparently, the filter method doesn't realize that we are operating on some form of sequential sequence, in ordered sequence. So it will work properly, but it will evaluate all elements in the stream. And that's problematic, because actually, after a few elements, we already know that all future items will never match the predicate we supplied, and won't work with infinite streams, which is pretty important. So let's have a look at how it works in practice. So we can call this, it works, but again, it evaluates not only first 3 elements, but also all of them, to make sure that we never encounter an element that doesn't match the provided predicate. This is a very simple thing. This can be problematic because of performance, and if you don't want to have this problem, well, you need to migrate. You need to migrate beyond the JDK 8. Because there were solutions, very small, supplied that deal with this kind of problem. So, for example, Java 9 brought methods like stream, take while, or drop while, which provide exact semantics that we are looking for. So, if you really want to stay with JDK 8 and use this functionality, there's no way you can do that. You need to go back to your old school for while loops and so on. But even if you want to do that, sometimes it's a really good idea to use a limit method to make sure that at least you don't end up evaluating infinite stream, well, infinitely. So the small change became as easy as replacing filter with the new method. And suddenly it turns out that everything works. Okay, so that was a very simple example. You might be thinking that trivial, but we will revisit it in a second. So here comes my favorite part of Java 8, which is the stream flatmap method. I'm not saying it's not my favorite because of the concept, but because it features a very bad bug in the implementation that got fixed later on. So in order to understand that, let's revisit what streams are. So streams are not classic data structures. This is more like a fancy form of an iterator providing a functional API. And the very important feature of them is that they are lazy. This idea is borrowed from other functional languages. This is kind of a concept of a lazy sequence. And the very important idea is that the laziness makes it possible to short-circuit certain operations and be as performant as imperative code. Well, as performant regarding the time complexity. And, well, in theory. So this kind of a code, you probably know a lot, those patterns, can be easily replaced with stream sequences, but there's a certain misconception, because many people, when they see this form of a code, they might assume that this is very not performant, because suddenly we take all elements, we flat map all of them, then filter, only to take one element. But the fact that it's lazy allows you actually to be as fast as this one, because we can simply short-circuit, take first element, and return it, at least in theory. Plus, you get this very cool feature. The cohesion is much better, because you have all things in one place and in the right order, and not scattered all around the place. Let's see, you start with errors, then you define some counter that you increment it in 3 different places, and then return it. That's really ugly. But there is a big problem in Java 8 because of the bug. So let's start with some very simple example. So while keeping in mind the fact that streams are lazy, let's do this very short, easy task. So let's take a first encountered address of the first encountered user. Simple, right? So as you can see inside, we have a list of one user with a few addresses that are modeled as simple strings. Then you can do this very easily using Stream API. So we go for the flat map, we go for find any, and again, what do you expect to be printed out if we add this one method over there that allows us to look which elements go through the Stream API? So, what do you think is the right answer? Oh, sorry, I spoiled it. So, you might be thinking, I just told you that this is the concept of lazy sequences. They should be short-circuiting. But apparently, this is not happening. So we have a list of one user with 5 addresses. But what's happening over there? For some reason, all of them get evaluated. And this is a very important thing to realize, because sometimes it can even, well, in some extreme cases, can bring down the whole system. So imagine you have that this stream evaluated inside the flatmap method is, let's say, very costly. It might be infinite. It might produce a very huge object. Imagine that this is some network call that calls, let's say, you call multiple microservices around the place. And then if you try to see what's going on inside your JVM, you see that this very sad picture of your JVM crying. And you see, this operation, in normal world, let's have a look at the simple algorithm. We have you need to take first element of an infinite sequence. What's the time complexity of that? Well, 1, okay, because you take the first element and you don't explode. But apparently, this is not the case with streams implementation. So you might, and if you have an infinite stream, this will keep going on forever. If it's very big, it will just evaluate all elements being in this sequence. So, as you can see, this operation should complete pretty much immediately. But instead, it's producing this very sad image of what's going on in there. But it can get worse. Because imagine that if you have a flat map over there, and then you chain some other map methods that might do some very expensive calls, it turns out that those get evaluated as well. So it's super important to realize that this is the problem, that there is a problem. And if you look at the implementation of the Stream API inside, well, you might not be able to see that. Let's zoom in. Inside, you can see that inside the flatmap method, there's, instead of an iterator, there's a very straightforward for each call. And this is the problem of all of that. So whenever you are going for a flatmap operation, internally there's a for each, and your short-circuiting is gone. Your laziness is gone. So that's not perfect. Well, you can kind of fix it by yourself by writing your own splitterator-based lazy flatmap. Well, it's not very readable probably for you, but even if it was clear enough, probably also would be hard to comprehend. So yeah, that's the result. But the practical solution would be simply to go to the future and migrate beyond JDK 10, because those small things suddenly got fixed over there. The interesting part is that the bug was filled quite a long time ago. You know, like I think a few months after JDK 8 went public. And when you might be asking the question, why wasn't it fixed? Because for quite a long time, it wasn't recognized as a proper bug. Because if you look at the documentation, you can read and see that there is no mention about this method being lazy. So, you know, technically, it's not a bug, but it is in practice. So, not perfect. So, if you really rely on this kind of lazy evaluation, well, you can't get it in Java 8. So either you drop Stream API or just migrate. Same for Java 9, because you don't have it over there. So Oracle lawyers managed to convince us that this is not a bug. And in Java 9, it was kind of fine, because because nothing changed. But when Java 9 was released, and those two methods that I mentioned at the beginning, this is where fun starts. Because let's revisit the take while implementation. So in Java 8, it's not a bug. We go to Java 9, we got take while and drop while, which terminate conditionally after a predicate is not matched. So let's have a look. Let's do a very simple test. So we have this very simple list. There's a list of two lists. One first contains 1 and 2, second contains 3, 4, 5, 6, 7. And now, just tell me, what does this code print? Yes, that was a question. Come on, it's easy. Okay, you have two nested lists, 1, 2, 3, 4, 5, 6, 7. You flat map, it's a hard word, flat map it, you forage it, and you get 1, 2, 3, 4, 5, 6, 7 flattened collections. As simple as that. Okay, another simple example. We have a stream of 1, 2, 3, 4, 5, 6, 7, and we take all elements till we not encounter a 4. Okay, what do we get there? 1, 2, 3. Perfect, another very easy example. And now, let's combine those two together. So we have both examples combined. So we have a nested list, then we follow with a flat map, and then place take while straight after that. What do we get? 1, 2, 3. 1, 2. Okay, let's have a look. So we get something that probably none of us expected. We get 1, 2, 3, 5, 6, 7. So apparently something that wasn't a bug in Java 8 started being a bug in Java 9, because we started getting those very unexpected and incorrect results. So unfortunately, we were promised that this tool was that cool, but it turned out that, as always, unfortunately. But, well, there's another pragmatic solution to this. Well, migrate to JDK 10, because this small feature got shipped there. You might not care about Java module system and maybe parallel for GC that was introduced in Java 10 as well. But those small features actually matter. Another thing. Have you ever tried playing with Lambda expressions and checked exceptions? That's kind of painful, right? So the way that the Lambda expressions are represented in Java is by using functional interfaces. So they took the old idea of using anonymous inner functions and passing them as interface implementations that were our old school Lambda expressions. And now we can simply use lambdas to populate those methods that are over here. But there's one problem with that. Because you see, there's the method apply, and here. You see? Nothing is here. So if you have a Lambda expression that inside the body throws a checked exception, it forces you to manually actually try catch and do something with that. So forget about those nice method chains. We end up in situations like this. And well, if we try catch something, well, and if we don't really care about this exception at this point, maybe we care about the exception thrown by the whole expression. Well, you need to put another one. That's not perfect. So you have two options. Either you repackage it or just swipe under the roof, the carpet, sorry. Roof, oh, come on. So that's not perfect. And there were many libraries that actually tackled the problem, because this can be simplified a bit by preparing custom wrappers that allow you to repackage every exception into a runtime exception. Actually did one of these. But this is just a syntactic sugar for dealing with the problem. And it's not perfect. But let's, for a moment, try to outsmart Oracle and their lawyers. So if you look into Java language specification, I think 18th chapter, you can read a very interesting note. So a bound of the form throws alpha is purely informational. It directs resolution to optimize the instantiation of alpha so that, if possible, it's not a checked exception type. And what does it tell us? So in other words, whenever we use generics, and whenever we try to generify exceptions, those will be generously inferred to be a runtime exception if a more specific type can't be inferred. And we can actually leverage that knowledge and try to outsmart Java itself. So let's create a very simple method called rethrow. It accepts an exception and simply throws it. Does it work? Yes? Yes. Okay, let's try to generify it. We simply add a generic parameter all over here. Okay, makes sense? Makes sense, but doesn't compile because, well, we now have an unhandled exception, which is not cool. So what do we do then? Remember the note about being generously inferred to a runtime exception? Well, it turns out we simply need to cast this one into T. And suddenly, the compiler is not complaining anymore. So what we created over there is a method that takes a checked exception and throws it as a refroze it, but with unchecked, with runtime exception semantics. Pretty cool, right? So now we can use it anywhere we want, and we don't need to try catch it anywhere. And now, if we really wanted to put this into practice, we could, for example, create our own checked functional interfaces that have this throws clause all over here. Now we could create a method that repackages this one into adapter method that repackages the throwing function into the function itself, and then simply implement that. You call the method, you catch it, and then you rethrow using the method created that you saw a few slides ago. And suddenly it works. You can use checked exceptions in lambdas. Well, it has its downsides, because compiler doesn't know. Even if you try to catch the checked exception, it doesn't realize that it's there, so it will complain. But it can simplify your code quite a lot. I know it might be kind of fast to go through that, so there's a write-up where you can just slow down and slowly go through the whole thing to make sure you understand. But there is one very important note from Brian Getz that you probably should be very careful when using that, because it's not very safe. But on the other hand, is it safe to repackage all your checked exceptions in runtime exceptions? Well, it's up to you. Your call, what do you do with that information? And now, one more thing. One of my favorites, so parallel streams. This was one of the biggest things of the Java 8, because apparently the whole concurrent programming, parallel programming could be achieved in a very easy way. So, there are so many people were trying to scare us that this is a difficult thing to do, but apparently it's very easy. You just need to use one word, and you can leverage the power of parallel computing. So that's not perfect, but is it really like this? So the promise was made by leveraging declarative programming. Well, we don't need to worry about the implementation details of what's happening underneath. This is the cool part. So technically, we should be able to parallelize this very easily without affecting the people actually calling the declarative code. And yes, and it was done like this. Technically, it's just one word that allows us to leverage parallel computing. It sounds very beautiful, right? But is it really? Well, if it is, well, perfect. So we go to our projects, we go Ctrl+R, and we replace our .stream calls with parallel stream calls. And we experience infinite performance. Is it really like this? Why not do this? It turns out it's not that of a good idea. Because whenever, if you read about parallel computing, executors, thread pools, and all those things in Java, you always need to set up so many things, and suddenly there is nothing to set up, because you just have one method call. So slowly, multiple questions arise. So for example, where are those tasks run? In which thread pool? Maybe in the cloud, or maybe in blockchains, whatever. Or for example, so if it's run in some thread pool, how do you provide your own custom one? Or maybe what's the maximum number of tasks that can be executed in parallel? What's the size of the worker queue? And so on and so on. And as you can see, there are not that many answers in the documentation. But if you try inspecting the code, it turns out that behind all of that, there is a static fork join pull used behind the scenes. It was introduced, I think, in Java 7 along the fork join framework. And multiple questions arise. So first things first, it's an implementation detail. So it's not like it's mentioned in the documentation. There's no formal contract enforcing this to be the same case, well, here and in the future. So if you rely on this information and you migrate beyond Java 8 and suddenly it changes, well, you can't complain because no one promised that. So actually, the thread pool that's used for execution of the parallel streams is unspecified. But since we know that the fork join pool is used for this thing, well, we can actually look into the API and find the fork method. And it turns out the fork method allows you to execute this task, pretty much allows you to hijack the pool, hijack the task and put it in your own custom pool. And this actually works. So whenever you want to use your own custom configured thread pool, you can just create it manually. It doesn't give you that many configuration options. Then you submit your task, parallel stream task, within that pool. Again, that's an implementation trick, but it becomes actually quite interesting if you realize that there was a very important bug all over the place. So fork join pool, the common fork join pool, is static, is shared for the whole JVM. And now, well, where does it get its settings from? It asks the operating system for certain information, for example, number of cores. But here, you might, for example, manually specify the parallelism or other things. But apparently, when you do this trick, it will not take those numbers into consideration because it will still rely on the settings of the common pool. And that's not ideal, but again, got fixed in JDK 10, and even those, and it's a small thing, you might not be using that, but still it's very important to know because it can be pretty crucial. And now, one very important thing to mention is that, again, if you have one static shared thread pool for the whole application, it might be not a very good idea. Usually, when you want to parallelize something, you want to assign resources separately for all tasks. So, good to know about that. But now, if you really want to create your own thread pool, fork join pool, you don't have that many settings available because you can control the parallelism level. That actually, as you notice, doesn't really change much in this case. Well, you can provide your own fork join worker factory. You can provide your own uncaught exception handler and async mode. So it's not very configurable. But again, here comes JDK 9, and not many people know about this, but we got a new constructor for the fork join pool. And apparently now, there are way more configuration possibilities. So now, not only those 4 configuration params, but now we can set also core pool size, max size, minimum runnable threads, if saturation is allowed, and thread keep a lifetime. So as you can see, this changes quite a lot. But again, you probably shouldn't rely on this technique of submitting your own parallel streams into your own custom fork join pool, because again, it's an implementation trick that might not work in the future. And now, since we are slowly reaching the end, actually it doesn't make sense to parallelize all the things. Oversimplifying the problem might have encouraged you to actually go and use it as much as possible. But usually once you decide if you want to parallelize something, you should probably take multiple things into consideration. So, for example, this is a very simple example. This is your homework. So you have a very simple task. It's running sequentially. I hope you can see that. Then you go into parallel, and it becomes slower than the sequential execution. And you might be thinking, if you go parallel because of locking and stuff, it might be as bad as sequential. No, it can actually get even worse. But it's homework for you. See inside what's happening inside the random next int method. And the most important takeaway from that is that parallel doesn't always mean faster. So you might be thinking that I've done a very Polish thing. I came on stage and started ranting and complaining about Java itself. So the key takeaway might be just go to Kotlin or Scala because they are better or something. But actually, no. Because I wanted to show you all those problems that can be found in Java itself, but I really want to underline that all those problems get fixed along the way. So you might be not interested in the module system or the update to the garbage collector. You might be not interested in the var keyword in Java or other those small features that appear all along the way. You might be satisfied with Java 8, but all those small things that get shipped along the way might actually save your production, not once. So just remember about that the small things matter as well. And that would be all that I prepared for today. Thank you very much. You can find my presentation over here. It will be on Twitter very soon. And we are hiring. If you are looking for a remote job on Malta in a product company that pays in euros, let me know. OK, so thank you very much. And we have a bit of time for questions. Thank you.